Hello everyone, my name is Beiran, a PhD student from Trinity College Dublin. This work is about using evolutionary multi-agent artificial swarm intelligence to share resources in public cloud systems. This work is a collaboration work between Trinity College Dublin and Huawei Ireland Research Centre SRE Lab. In this paper, we propose a resource-sharing approach with artificial swarm intelligence to allocate resources in public cloud. In public cloud services, cloud hardware resources such as CPU, memory, disk, networking, etc. are virtualized before being provided to customers. The utilization of the resources are highly dynamic, and there are opportunities for users to share resources with each other to minimize the overall resource utilization and make all users satisfied. Our resource sharing approach provides a new option for IT operators to optimize their resource allocation with artificial intelligence. Our target is to design a sharing scheme that to give enough reward to the users who share, to make sure that the users do not experience service disruptions while sharing, and to give resources back to users when they need extra resources in some circumstances. However, we have many challenges to achieve satisfaction for all users because the demand from users is dynamic and the users have different personalities, and the number of the users is large, and so on. To cope with the resource sharing problem of large scale of cloud users, we bring in concept of artificial swarm intelligence, ASI. ASI is a multi-agent reinforcement learning method that provides solutions to imitate human or animal behaviors and personalities in a swarm and optimize the actions of the swarm. With the concept of ASI applying in a cloud resource allocation system, AIOps team of public cloud system is capable to achieve optimal resource utilization without compromising the QoE of the customers. We propose a evolutionary multi-robot personality model to design agents to act as cloud customers to do resource sharing between them. In EMP model, we define all agents into three types: rich agents, needy agents, and self-sufficient agents. During the resource sharing, the agents conduct three steps: evaluation step, sharing step, and the evolutionary step. In the first step, the system evaluates personality trait and state risk of the agents and select action for them. In the second step, the system reallocates spare resources between sharing, through sharing between the agents. In the third step, the agents evolve personality traits and adjust their type. This picture shows how our agents share resources in the cloud. RST means the remaining resources, which equals to the allocated resources minus the resources utilization by an agent. If it is a negative number, it means it's a needy agent. If it is a positive number, it means it's a rich agent. If it's zero, it means it's a self-sufficient agent. In our scheme, Each resource sharing step is preceded between a pair of one rich and one needy agent. During the evaluation step, we use the concept of reinforcement learning. We define probability of action selection, value function, probability of the agent in risky states. Risky states means the agent does not have enough resources. We also define the personality traits that affect the agent's selection. An agent decides share or get resources with another agent depending on their personalities and the real-time resource requirements. During the sharing step, we use asymmetric large bargain solution. We calculate the bargaining power of each agent. That helps the agents to make deals and determine how much resources are shared from one rich agent to another needy agent. After the sharing step, we have evolution step for each agent. The reason is that after the sharing, the agents have changed their state risk levels. When the demand changes in the next sharing round, the agent will have a different situation of resource requirements so that personality traits of the agents will evolve. Apart from the main EMP model mentioned before, we designed two more models, SEMP and NBSS model. Compared to the EMP model, SEMP uses different schemes for evaluation and evolution. Agents neglect the evaluation of the state risk probability regardless the consequences of the chosen action. In NBSS model, all agents have the same personality traits and it does not evolve. This table compared our proposed three models, EMP, SEMP, and NBSS. EMP including two sub-algorithms, EMP underscore A and EMP underscore F. Considers both personality traits and seed risks. The difference between EMPA and EMPF is whether it uses AC metric Nash-Bargan solution or use fixed steps when proceeds one round of sharing. EMPA and SEMP use NABS sharing strategy and NBSS use the Nash-Bargan solution. We set up experiments to evaluate the performance. We simulate a 100-agent system for sharing resources in a public cloud. We define one resource usage measuring round as the time window between two consecutive instances of measuring an agent's resource usage. During each resource usage measuring round, each agent conducts multiple sharing steps with other agents to achieve the goal of eliminating all needy agents. We investigate two use case scenarios. The first one is independent sharing. The real-time resources usage in each usage measuring round is randomly generated, and the remaining resource from the previous round is not rolled over to the next round. The second one is continuous sharing. The real-time resource usage follows a sinusoidal, and the remaining resource from the previous round is rolled over to the next round. Figure 1 shows the experiment results for algorithms EMPA and EMPF in terms of the amount of spare resources before and after sharing in one usage measuring round. Each dot on the figure corresponds to one agent. The negative value of spare resources of an agent on x-axis means the agent's real-time resources is not sufficient for its usage, while the positive value means the agent has some spare resources. The results show that both algorithms help every agent in the system to get enough resource for the current need, as all the agents place at non-negative space on the right side of the figures after sharing. The blue dots. Figure 2a shows the process of reducing the number of leading agents during the sharing steps within one single resource usage measuring round for the four algorithms. The fewer sharing steps it takes to reach zero, the better the performance of an algorithm is. Figure 2b shows the sharing steps the algorithms take during 100 independent usage measuring rounds. Both figures show that an algorithm, EMPA, performs most efficiently as it uses the least sharing step to make the number of needed agents to reach zero. The performance of the other three algorithms are close to each other. Figure 3 shows the result of sinusoidal usage patterns during the time of the day. Similar to the previous scenario with random usage, the EMPA needs fewer sharing steps than other three algorithms to make the number of the needy agents to zero. The performance of the other three algorithms are also close to each other. However, in this continuous sharing case with sinusoidal usage pattern, the advantage of EMPA over the other three algorithms is more obvious than the independent sharing case. It's reasonable because this continuous sharing scenario is more stable and closer to the reality. We assume that in a public cloud system, the system gets real-time usage information measured every 15 minutes slot and schedule one sharing step every 1.5 seconds. The system can schedule up to 600 sharing steps in 15 minutes. We calculate and show the average percentage of satisfaction time for all users in Tab 2. The EMPA has the highest percentage of satisfaction time as 95% during the sharing. However, without sharing, the percentage is only 69% in random usage pattern and 63% in sinusoidal usage pattern. The other three algorithms have similar performance of around 85 to 88% during the sharing, which is higher than the case without sharing but not as good as the EMPA. In conclusion, we integrate the concept of artificial swarm intelligence and personality traits to design a multi-agent system on the resource sharing of the cloud system. We have designed and implemented our main algorithms, EMPA, as well as three other algorithms, EMPF, SEMP, and MBSS for comparison. In the experiment, we simulate a 100-agent system and executed 100 usage measuring rounds with two different use case scenarios. The results show that all algorithms are capable to reallocate spare resource to the needy agents through the sharing procedure between the agents without adding external resource. The EMPA performs much better than other three algorithms in terms of fewer sharing steps as well as higher user satisfaction rate. Our proposed resource sharing models bring a new scope for AIOps researcher in public cloud for research optimization and management. This publication has emanated from the research supported by Science Foundation Ireland, and thanks to Huawei Island Research Center SRE Lab for the collaboration. Thank you.